So now that we've talked about aeolian material, which can be input from deposition or removed from erosion, let's think about what might happen actually inside our box of Hillslope material, or perhaps at its bottom. So in these above cases, we've assumed that there's an infinite supply of mobile material that can move up and down the hill slope, but sometimes this isn't the case, right? Not every hill is an infinite pile of sand. In fact, many of these hill slopes that we look at in reality might actually have a thin carapace of soil that lies over, a subsurface that's made up of bedrock. And so this bedrock subsurface might be more or less in place while the hill slope is, creeping. So if we want to understand how this whole system works together, let's return to this box analogy that I had. So where we look at some box along the hill slope and think about what's going in and what's going out. One difference, though, is that with the aeolian processes, we could talk about how the actual elevation of the surface was changing, because we were putting stuff into the top or taking it off the top. In this case, we can't do that quite so easily, so we're going to talk instead about the H, this thickness of the mobile material, and that this thickness of mobile material is changing over time. So we have above the change in thickness of mobile material as a function of discharge downslope. We also talked about the weathering processes, and overall we have this dH sub m, so change in thickness of mobile material and over change in time. That's equal to the amount that's coming in from creep minus the amount removed by creep, also from aeolian processes, and also from weathering. And let me go up, because the notation I was using before when I wrote these notes is not totally clear to me right now. So what it looks like is that let's analogy to equation 16 and 17. So it looks like actually I've miswritten this one. So let's just cross this all off. I'm going to go back and fix the notes on that. But what I really want you to focus on is this idea that we have a change in thickness from weathering. And we have, what this is supposed to be really, is a change in thickness of mobile material from aeolian processes is going to be equal to A, and change in thickness, and also change in thickness per change in time from discharge is equal to d squared z over dx squared. And so here there's just a little bit of a typo where there's supposed to be a line break right there. So I've got to go back and fix that. All right, so we have those two terms right there, and they combine with this weathering term to create this creep term, this an aeolian term, weathering term, that all are summed together to be able to give us, yes, and I forgot this k here too, k sub m, k of mobile material, and those three combine to give us the term right here, which is the rate of downslope transport, and plus the aeolian inputs minus the aeolian outputs, plus the weathering inputs minus the weathering outputs. And so this all seems straightforward. It might seem like the weathering process is just pretty similar to what we were talking about with the aeolian processes, wherein we have some amount of extra material added that's thickening this box, and some that's taken away that might thin it. And right now we're talking about the bottom of the box instead of the top, but maybe it's pretty analogous. But we do have some complications. And this first one is the one that I was just mentioning, that we're solving for the thickness of the box. So how do we convert this to solve for the elevation of the surface, and therefore compute the shape of the full hill slope? Because what we really want to do as geomorphologists is know what the shape of the landscape is. And we have like a hill, right? So what causes its surface to be like that, and what maybe causes its soil thickness to be like this, or mobile material. Second question is, do we have any way of knowing what controls the weathering rate and including it into the equation? And you might remember that we talked about this thing called the soil production function. Well, we're going to see that again. So because of that, we have these two different subsections below. And this first question we're going to answer in 2.7.1. And the second one we'll answer in 2.7.2. So to start out here, with weathering and land surface elevation. So mobile material on hill slopes typically has porosities that range from just a few percent to several tens of percent, so it could be quite large. Solid unweathered bedrock, on the other hand, generally has very little to no porosity. You can think about bedrock and the fracture patterns it has. So some near surface bedrock does have some fracturing, maybe a percent or two of pore space, but often very, very little, and often just a fraction of a percent. And so if we have a hill slope that's related where the mobile material is removed from bedrock via weathering, there is a whole range of different porosities that are possible for this mobile material, but not so much for the underlying rock. And so what we can see here is that we have gravel, sand, silt, and clay with their porosities. And now we have these things like fractured basalt and karstic limestone. Those can be really porous. Sandstones can actually be relatively porous, so there might not be much of a change there, but going from like a sandstone to, let's say, a sand deposit. On the other hand, many of these other rocks have very low porosities, and if we think about dense crystalline rock or fractured crystalline rock, they might have 0 to 10% porosity, and this is often what's underlying hill slopes in the mountains. So in the core of mountains, when you're away from the sedimentary cover. So depending on the ratio of the rock porosity and the deposit porosity, there might be some amount of inflation of material, right? So we might weather, let's say if we weather a meter of dense crystalline bedrock, that might actually produce significantly more unconsolidated material, especially if it's weathering to something like a clay, that it has a very high porosity. So that extra porosity means that you're going to expand the actual thickness, because some of that new thickness is air and some of it is actual rocky material. And so through conservation of mass, we're going to evaluate whether the thickness of the mobile material layer, HM, how that increases or decreases at the rate the rock's weathering. And that's what we were just talking about right now. And what we're going to do to figure this out is to define a bulk density of hillslope material, which is the mass of solids, and therefore neglecting the fluids that fill the pores, for both the rock and the mobile hillslope material, rho sub m. If mass is conserved within this rock mobile material continuum, then we have the following set of equations. So we have rate of change, or rate of change in thickness of the mobile material is just going to be equal to the weathering rate. Now the change in the elevation of the rock surface, and so here we are. So we have Z is the surface right here, Z sub R is the surface right here. We have rocks down below that, and we have our mobile material up here, is going to be equal to negative the weathering rate, and so this is going to be going down through time as the thickness here is expanding. And it's related to the density of the mobile material divided by the density of rock. And so if the mobile material is less dense than the rock, this might not be going down as fast as this section here is growing. And so therefore, if we combine those two together, so we have Z dot is going to be equal to change in elevation of the rock plus the change in the thickness of the material. We plug this one in and we plug this one in. We actually then get this weathering rate times 1 minus rho m over rho r. And typically, the density of rock is going to be higher than the density of the molten material. And so therefore the elevation of the Hill surface may often rise due to these weathering processes. However, there is another process that might counteract this rise, and that's something called dissolution. So this results in the material being removed from the hill slope, and so here we've got to consider these effects of dissolution on the layers of molten material. So sometimes we might just have some mechanical kind of fluffing up of the sediments, and that could create this lack of density when compared to the bedrock. But it's also possible that we instead have some dissolution that's removing material, and so we're actually losing mass out of this box. And so the rate of dissolution is calculated across the whole box. So it's going from 0 to h sub m, so 0, h sub m, and then from x naught to x naught plus delta x. Not a delta. There we go. And so this d here is italicized, and this is going to be our term for dissolution. And so we're integrating it over the entire area because that's how the area on which it acts. And so what we can do here then, so if we have this double integral, we're going to go from, so I'm just going to rewrite it, 0 to h sub m, integral from x naught to x naught plus delta x of d. And I'm going to underline this d just so we know which one it is. It's not part of the dx or the dy. And so let's solve this inner integral first. And so we're going to take a bit of a shortcut since we already did this with the Aeolian system. Actually, no, just for the sake of completeness, let's do that in a full way. So we're going to evaluate this guy between, so we have dx on the inside, integrate, dx turns into x, d is independent so it stays as a constant, so dx between x naught and x naught plus delta x. And so over here then we get d times x naught plus delta x minus, over here, x naught, so equals d delta x. Great. Now we can run through that whole process again, and we can say that we have d delta x, then from 0 to h sub m dy, so times y, 0, h sub m. This is even easier, d delta x, h sub m. And then if we want to know what's happening in the individual column of the box, right? Oh, that should not have been a squiggle, that should have just been a straight line. Delta x wide, h sub m high. Then what we get here, if we're looking at this individual column, is the need to divide this through by delta x. And that's where we get this change in thickness as an effect of dissolution is equal to minus h sub m times d over delta x, and this minus here is this convention. Loss. And so what we're saying is that if there's dissolution, there's loss of material from the hill slope. And so therefore, we're actually losing elevation if we dissolve material. So interestingly here, right, because we're only differentiating with respect to x when we're thinking about this, delta x term and trying to make sure that we're thinking about just this small limited box area, the height of the box remains in the equation. So what does that mean? What that means is that if the box is taller, there's a greater length over which dissolution might take place. and therefore this process might become more important if we have more mobile material. Of course, it also just depends on what the dissolution rate is, and that could also be related to how thick the total soil column is. So, all right, so let's take our former equation here. So we have weathering, and now we have dissolution added. And so now we have, this is going to be the diffusional term. This is the aeolian, so this is the Hillslope creep. Aeolian inputs or outputs. Weathering of the bedrock into the Hillslope mobile material, and then dissolution of material in the mobile material, and conversion of it into some sort of solute that is removed from the system. And right here, I just want to point out that I'm also only considering dissolution in the mobile material. Of course, there is dissolution of material in the bedrock as well as part of this process that initially breaks it down and builds saprolite, but we're not considering that in this certain equation. But from the tools that you've gained here, you could certainly start to look at that and think about how that might affect the actual density of the bedrock and initial conversion of the bedrock into mobile Hillslope material. So this equation is a little trickier to solve because you need to know the thickness of the mobile material column. And that thickness actually evolves as the Hillslope evolves. And so that creates this potential for a feedback loop. And therefore, we might need a little bit more information. And that extra information can come in the form of some initial conditions, and then we kind of run a model forward through time and look at how this mobile material thickness changes. Or it could come in terms of just a special case of the solution in which the mobile material thickness stays constant through time. All right, so that's this first part that has to do with density and whether it fluffs up or compresses down. But the next piece here, we have to start thinking about the humped and exponential functions, so these different functions that show us what soil production rate should look like through time. And I'm just going to do a quick advertisement here. Cambridge University Press is so kind to make these figures freely available online for educational purposes. And so this is from Anderson and Anderson. And this Anderson was my PhD advisor. So it's a great book. If you guys want to, you should go out and get it, or see if you can find some library access online. It's a really excellent geomorphology textbook, and it's what we would usually use if we're in person. But because we're doing this all online right now, I'm considering just going with these notes alone. If these notes, these presentations end up being part of a hybrid curriculum in the future or some sort of flipped class, then I think I'm probably going to zoom back into using that textbook as well. And so they talk about mobile regolith, and that's because regolith means this material that's been produced in place that's mobile, and so that's what this exact thing is. So regolith is going to be material produced locally. I say mobile material for the mobile stuff on hillslopes because that's the most general way of thinking of it, but in most landscapes, most of these bedrock landscapes, the material that's making up that soil column, or might not even be transformed into soil yet, is regolith because it's coming locally from this from that landscape. So what do these say, right? It says that when regolith thickness is low, or when mobile material thickness is low, there's generally either super high or slightly low but non-zero production rate, and that decays or maybe makes some local maximum, and then eventually just decays as thickness increases. So that's so that gives us some additional information as to how quickly the weathering is happening. Let's start to throw that into this weathering rate inside our main equation. So over here is just what we were talking about before, exponential function and hump functions. And the way that we get to those functions is actually from data. So these are exponential fits for rates of bedrock weathering. And so you can see over here, all of these points are showing us zones where there's absolutely just bare bedrock. And so the weathering rates are going down. There isn't any freeze-thaw action or fluid. There's not much in the way of fluids in contact. But even with like a teeny tiny amount of soil cover, weathering rates shoot up pretty fast, right? So the hump function might look something kind of like this, where there's a weathering rate, and then this is depth of material. And those data above are gained from working with cosmogenic radionuclides, which are able to track erosion rates and help us with dating. And I'm not going to get into that right now, but that's just a really important tool that we have in geomorphology. So based on this above discussion, the rate of weathering is a function of thickness of the layer of mobile material. Because this function, so what we're going to do is actually look at this exponential function, just because this is actually a little bit easier for us to handle in a differential equation, and also because it looks like we really don't get down to these super low rates unless we totally lose the soil column. So we're just going to pretend we have at least a tiny itty-bitty bit of soil. And so we're going to go with this exponential function for soil formation. So weathering rate is going to be equal to some W naught. So this is the surface weathering rate. E is Euler's number, so this is the, like for an exponential function. And this is the thickness of mobile material over some length scale, delta Z, and so this is our decay length. And if you're familiar with something like a half-life for radioactive decay, it's the exact same idea. And it's just saying, like, does this function up here, crash down really suddenly? Or does it actually take a very, very, very long time for it to decay? So this here now actually adds a second feedback. So we already had this dissolution feedback between thickness and the mobile material thickness, and the height of the surface of the landscape. This adds the second feedback. So let's see what we have here. So we have this thickness of mobile material over change in time, and once again, creep, aeolian, weathering, and over here on the right-hand side is the dissolution. And so if we look at that, we can start to think about some of the other pieces that are important. So we can look at what the elevation of the rock is over time. So this is mobile material, rock surface. And then we know that the change in elevation over change in time is the mobile material thickness plus the elevation of the rock surface. And so we just add this piece in here. And this also relates to the weathering, right? And so we have, and it also actually has then this exponential term associated with it, because we're dealing with the fact that the weathering rate is part of what is removing the rock. And so we add that in there, and that basically just amplifies the weathering by this density-related term. And so using this equation 36 right here, yeah, we've gotten a 36 equation, that's right. I'm just going to box this whole guy off right there, because this is your kind of final Hillslope diffusion and everything else mixed in, kitchen sink equation for how these hillslopes evolve. So using this equation, what we can do is start out by prescribing an initial topography, so some sort of like elevation as a function of distance across the landscape. Prescribe some initial mobile material thickness distribution, whether it's super teeny tiny or really deep, and then we can actually allow those to evolve and watch how they'll evolve through time as a function of aeolian inputs, of slope that's going to cause diffusion, of weathering that's going to create more mobile material, and of dissolution. So with this, we've gotten through our core equations for how hill slopes will evolve.